Okay, so let's try some problems together. Guess what? We got a box on a ramp. Oh, yeah, that's right. Box on a ramp. Did you think it was going away? Never, never the box on the ramp. We're going to be doing the box on the ramp in quantum physics. You watch. Okay, so let's look at the whole box on the ramp here. I got a box sliding down a ramp. I want to find how fast it's going when it gets to the bottom of the ramp. Okay, here's what I'm getting at with conservation of energy. You could do this problem with the whole FBD, F equals ma, component vector situation where you do like your gravitational force. Is being weird, but you could do like, get your FG straight down, find the FGX, find the FGY, figure out that your normal force is like a weird situation. My pen is all screwy. Yeah, and you could have all that SOHCAHTOA fun and figure out like the acceleration down the ramp and do like a SUVAT down the ramp. You could do all of that, but I don't think you have to. If we know conservation of energy, we can really kind of simplify this. Here's what I'm gonna do. Initial energy plus work equals final energy. I have an initial situation and a final situation, or a start and an end if you prefer. I'm thinking we should probably have said here, oops, slides down a frictionless ramp is going to be the idea, at least for now. So the idea is going to be that there's nothing taking away or adding energy besides gravity, which we account for with gravitational potential energy. There's no like adding or taking away energy outside of my system. So I can do like a conservation of energy thing here. So the energy I start with should be equal to the energy I end with. So let's look at how this works with conservation of energy, and it makes life so easy. Okay, I want to look at my start situation. I have a box up on top of a ramp starting at rest, and I want to think about what kinds of energy I have there. Okay, in the beginning, I want to think about, do I have any kinetic energy? Well, nothing is moving, so no. Kinetic energy, none. Do I have any potential energy? I think I do. I think I have gravitational potential energy because I'm up off the ground. So I should at this point decide where I want to make zero potential energy. The way to make life very easy is to say, let's make potential energy equal zero on the ground here. That seems like the thing to do. Yeah, so we'll say, let's call this zero potential energy, which means then if I want to find the potential energy here, I'm going to do MGH. We'll save put in numbers for later. But I'm up some H off the ground. This is going to be H. So I have potential energy because it's up here. Do I have any elastic potential energy? I don't think so. There's no string or spring or rubber band or anything like that happening. It'll be pretty obvious when you have elastic potential energy. Definitely not here. That's the beginning. That's going to be my initial energy. Now let's think about the final energy. So here at the end now, I say what's going on energy-wise. And this is going to help me find this. At the end, I want to ask again, is anything moving? Because that's how I know if there's kinetic energy or not. Well, yes, this thing is now moving because it rolled down or slid down the ramp. So the kinetic energy, it does have kinetic energy. It's going to be 1/2 mv squared. And I'm thinking this v is what I'm going to be solving for. Is there any potential energy? Meaning, first for gravity, is anything up off the ground? Well, no, not anymore. Now the box got to the bottom. The box is on the at the bottom of the ramp here, especially because I'm like measuring from the bottom of the box, it looks like. I've gotten down to ground level, so I'm at zero potential energy, gravitational potential energy. And there's still no spring, no rubber band, nothing like that. So I also have no elastic potential energy. All of this added up then is my final energy. Yeah, so that's the idea. You look at what's happening at the beginning, figure out your total energy, look at the end, figure out your total energy. This example and the examples we're going to do here for like our intro, it's just one object. You can do this and often will do this for a system with like multiple objects. So if there's multiple things moving around, you have to add up the kinetic and potential energies of each thing. So that's what we mean by system. This could be the total energy of everything in your system to start and the total energy of everything in your system at the end. So if there's multiple objects, you do this multiple times for everything in the system. beginning and end. Is it moving? Is it off the ground? Is there spring stuff happening? Okay, and I don't think there's any work here because it's not telling me anything about anything other than gravity or a spring adding or taking away energy. We're saying there's no friction here, so this whole thing is going to be 0. So I have a classic conservation of energy situation where I really do just have the same amount of energy at the end and at the beginning. Nothing changed along the way. Okay, so for the initial energy, I add up all the energy I started with, which here was just mgh. I only had gravitational potential energy at the beginning. And now I'm going to look at my final energy. I only had kinetic in this case, 1/2 mv squared. Okay, this happens a lot. You get used to this situation where you do like potential equals kinetic or something. It does happen a lot. This is not a rule. This is just what this problem happens to be. If there's multiple types of energy, we're going to have to deal with that. If this thing was like moving already at the beginning, I'd have some initial kinetic energy plus this potential energy equals my final kinetic energy. All right, so just be careful. But anyway, this is my setup for this one. I notice I can make math life a little easier by canceling out an m. That's fun. So I don't need this 10 kilograms, at least not yet. And let's see, I want to solve for the velocity of the box when it reaches the bottom of the ramp. So here I go. I'm going to multiply both sides by 2. So I get v squared equals 2 times g times h, because I'm solving for this here v. And I think I just want to square root both sides now. So the speed at the bottom should be the square root of 2 times g times the height being the height above 0 at the beginning. That's going to be 0.5 meters. Okay, now I've got my answer. And I should do the silly part, which is plug in numbers and get a number. Okay, so let's do it. 2 times g, we're going to do good old 9.8 meters per second squared, because we're assuming this truck is on the Earth and not Mars or something. The height I started at was 0.5 meters. Okay, nice and easy. 2.5, even more fun. They cancel out. So I'm really just taking the square root of 9.8, I'm thinking. And I put that in my calculator, and I get that the speed at the bottom is 3.13 something 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 meters per second. I've got 3 sig figs, so I'm going to stick with that, 3 sig figs. So the speed at the bottom is 3.13 meters per second. Yeah, so there you go, conservation of energy. I don't have to do any SOHCAHTOA or break forces into vectors or anything fun like that. I just do initial energy equals final energy. Good to go. Okay, let's keep going with the few. Let's say now that box keeps on sliding. Again, in this magical frictionless world that we like to live in when we do physics problems sometimes. And it hits a spring. Of course it does. Now the box crashes into a spring. And so the box is going to like, hit the spring. This thing is going to compress, I'm thinking, and is going to momentarily stop the box. If you can picture that. The spring constant of the spring is like a number given here. I want to calculate the distance that the spring is compressed by the box at this time. Okay. Here I definitely want to like make a sketch because I have sort of a beginning situation. So maybe I'll steal this. I'll keep this for like my start. But you always want 2 sketches. You really do want to start and an end so you can picture what's happening. So at the end, what I think is happening, actually, I'm going to do it this way just so I can picture a little better. I'm going to draw like above and below. Just because then I can kind of line it up. Try to if my pen would cooperate. Yeah, but anyway, you want to really, really, really draw these, sketch these out as best you can. Picture what's happening because it really, the whole skill is about picturing where is the energy in the beginning and where is the energy at the end. Okay, that's going to have to be good enough. All right, now what's going to happen is I think this box is going to smash into that spring and is going to like compress it. That's what we're kind of mean there. It's going to compress it a good bit. And so this thing will get, bunched up, pushed in a little bit more. And when we say delta x, if that's my original 0, that's my original, we're going to eventually call this the equilibrium position where it like naturally wants to rest. This distance is my delta x. That's what we mean by that. How much do I, in this case, compress the spring by? What's the change in the length of the spring That's really the energy thing that's happening. Yeah, so okay, my box now is here, pushed up against a spring. And this is sort of my end situation. I can also label some stuff. I know it momentarily stops the box. So this is the moment, if I can, like, I'm trying to picture in my mind's eye what's happening. Box crashes into the spring. It compresses it. I think it's slowing down as it compresses it. And now at this 1 split second in time, it's like compressed as far as it's going to compress because the box is at rest. So right here, the V is going to be 0 of the box. Split second later, it might go flying off backwards or something, but this is the point in time I care about. This is the point in time I'm going to sketch as my end position. All right, and I want to calculate the distance that the spring is compressed, and that would be this, delta x. That's what I'm talking about. So my unknown is delta x, my compression distance. Okay, same deal here. I want to look at initial and final energy. All right, first question. When I look at the start, the initial condition, is anything moving? Yes, the box is moving. So I do start with some kinetic energy. Put it this way. I start with some kinetic energy, so I'm going to account for that. Kinetic energy is 1/2 mv squared. Is anything up off the ground? No. So my gravitational potential energy is 0. Is anything compressed against a spring? Not yet, right? Looking at this picture, and it's not touching the spring, so there's no energy stored in the spring right now. So here we go. There's my initial energy, right? Let's look at the end now. Let's look at the final energy. What's going on? Is anything moving? No. In this case, now when I'm looking at this point in time where it's at rest, there's no kinetic energy. How about potential energy, gravitational? I think not. Still on the ground, which we're calling 0 potential energy. But now this is the example of where you do have elastic potential energy. Because I am compressed. The spring is compressed. That's what we mean. Now there's energy stored in this spring, which is part of my system. Okay, so this much. All right, so another pretty straightforward one where we're just turning one type of energy into another. So I'm still going to use officially my equation, initial energy plus any work done equals my final energy. Just going to kind of plug in now. Yeah, because my initial energy is officially the sum of all this stuff for every single object I have. It's just the box, and it's just got kinetic energy. I'm doing 1/2 mv squared. I think, again, there's no work done because they have to kind of tell me if, like, there's friction taking energy away or if somebody was coming and pushing this box to give it some extra energy or something, but that's not the case. So this equals my final energy, which is just 1/2 k times delta x squared. Okay, so it's really this equals this. Again, I'm just doing a straight up kinetic energy. All the kinetic energy of the box here turns into all of the potential energy of this spring. And I'm solving for delta x. So I'm going to get rid of these 1/2s because there's both sides, so that's kind of convenient. So I want to get delta x by itself. I guess I'll divide by k first. So delta x squared. And let me write it like this. This notation is confusing, but delta x is all one thing. It's not like delta is its own thing. So delta x is this one variable. So I'm doing that squared equals mv squared over k. So then delta x would be the square root of all of that stuff. And now I have my answer, and now I can plug in the silly numbers. Here we go, square root. All right, we said on the last slide that mass was 10 kilograms. We also found, can I go back, that V is 3.13 meters per second. And we're saying here that K is 30 newtons per meter. So let me plug this into my trusty calculator here and see what I get if I punch all that in. So I'm doing oops, I didn't square this. This is squared, right? V squared. I'm doing 3.13 squared times 10. I'm dividing that number by 30. And then I am square rooting. So I get something like 1.80, I'm thinking. 1.807106, blah, blah, blah. Again, I'm looking, I have 3 sig figs here. I think I had 3 sig figs before. I'm going to stick with 3 sig figs, which means I'm going to round. So I'm going to have delta x is 1.81 meters. It compresses this thing by almost 2 meters. There's a big old box, and that's a somewhat floppy spring there. 30 newtons per meter. That's what I get. Let's do one more example. A classic roller coaster problem here. So we got ourselves a roller coaster going down a hill, doing a little loop-the-loop, coming up to some other hill. And we're given some information about point B, which I got right here. And then point E, which I got right here. So the problem kind of has set up for me what will be the start and end, because I want to say I have information about B. I want to find information about E. So I'll have to set it up like this. And conservation of energy is definitely the thing to do with these types of problems. I have a speed. I'm generating some heat energy with friction, so I'll have to take that into account. I want to find the speed at E. It would be impossible to net force this, to Suvat this with all the changes in direction and changes in acceleration that are happening. But conservation of energy makes it super easy. So let's start with our sketch, because we're going to do initial energy plus work equals final energy for our conservation of energy. And so let's think about energy and the beginning at my starting point, which is point B. So at this point, the roller coaster starts up here going down the track, and it gets to point B. I'm thinking it's definitely moving at point B, so it definitely does have kinetic energy. And it's up off the ground by some distance, 60 meters here, so it also has potential energy. There's no spring situation, nothing stretched or compressed, so I don't think there's any elastic potential energy, but we definitely have gravitational potential energy plus kinetic energy. Okay, let's just jump to the end then and think about what's going on at the end. I want to find the speed at E. It makes sense to me. The roller coaster's still going here, so there is kinetic energy at the end. And also, I'm up off the ground, so again, there's also, this should be K, obviously. At the end, this is, it's up off the ground, so it also has gravitational potential energy. So I got both types, both places. I'm just going to have to look at the amounts and make it math. The other thing I'm going to have to take into account is this. I got 65 kilojoules of heat energy generated by friction between points B and E. So as you go along the way, along the track, you're generating some heat energy, which I think the idea is going to be we're losing energy all along. That's the deal with friction. Friction, you always lose energy to friction. Friction generates heat. That's what happens when friction acts. Rub your hands together real fast. You can feel it. But so friction is always going to do negative work. Not that it destroys energy. It just changes its form. It changes it into heat, which is no longer useful energy, mechanical energy in our system. So that's going to be a negative number is how we're going to deal with that. Okay, now let's plug in now that we know what we got going on at these different spots. So initial energy, we said we have kinetic and potential. So I have 1/2 mv squared as well as mgh. I'm going to put some B's and E's on these to keep track of what's going on. So VB will be the speed at B because I want the initial energy there. And it's also got mgh. So I'm also going to call that HB, right? So this is the energy. This is how much total energy I've got to start with. I'm doing initial energy. Then I need to add the work. The work is this 65 kilojoules. Watch for the kilo. That means 1,000, right? But also because it's friction and it's taking that energy away, I have to think about this part. It's 65,000, but negative. So I'm going to write it like this, negative 65,000 joules. I'm adding, in other words, I'll subtract it from that side. And that equals final energy, where we said we still have kinetic energy, 1/2 mv squared. Now I'll throw a little E here to keep track of what I'm doing, that's now the speed at E, which will be different than the speed at B, because the height at E is different than the height at B. Okay, and I always want to think about what I'm doing and why I'm doing it. Well, the point of this is to find the speed at E. So this is my unknown. I'm trying to solve for this variable. I think I do know every other variable, so I really just got to do some algebra now, move this stuff around. Okay. Oh boy, let's see. I'm going to take MGHE away from both sides first, so I'm going to write it like this, just because we can look at something. So 1/2 mvb squared plus potential energy at B. I'm going to take it away here, minus potential energy at E, minus 65,000 joules, equals 1/2 m times VE squared. Okay, just pointing this out this way because this is a common thing, and this is why we had our delta H thing, right? This is the change in potential energy is really what this is, which is what our data booklet equation really gives us. I could think of this as mg times the height of B minus the height of E. That's my change in potential. Backwards, I guess. That's actually my backwards change in potential energy, since it's initial minus final. But I can simplify this equation, this bit of the equation like this a little bit if I want to. Anyway, let's put in our numbers. 1/2. The mass is 550. I think this is a fair place to plug in because now I'll see how much total kinetic energy I have at the end, which is a good sort of in-between check to see if these numbers make any sense. 15 meters per second squared plus, okay, I'm going to use this little bit simplified version where we factor out the mg, meters per second squared, times the difference, hb minus he, 40 meters, equals 1/2 m VE squared. Okay, and that gives me, I put in all those numbers, and I think I get 104,675 joules equals 1/2 mv squared. All right, there we go. That's how much kinetic energy I have at the end. I lost 65,000. I'm ending with like 104,000, so I must have started with like 170-ish thousand. These seem like about the right ballpark. So I feel like we're on the right track. So let us solve for VB now. So VB would be, I'll multiply both sides by 2. And then I'll divide both sides by the mass, M, of the coaster, and joules. And I think I need to then square root all of this. So this all goes under a square root, and I'll put it in my calculator. So lots of just plugging in and mathing now. Let's see. And when I do all that, I think I get 19.5099. We have 2 sig figs in the problem, so let's call this 20 meters per second is the speed at B. All right, there you go. So there's one where there's multiple types of energy at the beginning, at the end, and some work done along the way. So that's how you handle that. The other kind of thing that can come up, sometimes you might have multiple objects in your system. If that's the case, same deal. You add up all the kinetic and potential energy of every single thing that you're keeping track of at the beginning and at the end, and you plug them into this equation, plug in any work that's done, and solve for what you need to. Conservation of energy. It's so fun. It's so amazing. Can make life a lot easier. So practice a little bit. Have fun.